Hello, we're doing checkpoint 5.29. Let E be the region bounded below by the cone z is equal to the square root of x squared plus y squared, and above by the paraboloid z is equal to 2 minus x squared minus y squared. And we want to set a triple integral cylindrical coordinates to find the volume of the region using the following integration. All right, first of all, to find the volume, we note that the volume is going to be given by a triple integral over the region, whatever that region is, we'll call it E, and 1 dV. All right. Now, if we're going to go to cylindrical coordinates, we have to replace the dV with the extra r. And then we can write our integral with respect to z and then r and theta, or whatever order that we want. Okay, let's quickly get a picture of this. I mean, there's already a picture here, but let's draw that picture again. And if we really just focus on the picture itself, the region itself, without looking at the rest of it, we are just looking at the region that's this kind of a cone, ice cream cone-like thing. All right, and so if we're going to do this with respect to z first, we can draw a line parallel to the z-axis. Before we do that, let us also consider what's happening here on the xy plane, and because the xy plane is the shadow that we get, and that's going to be another important part of your cylindrical coordinates. And so the shadow that this is going to make is actually the intersection between the cone and and the sphere. So if the sphere is z is equal to square root of x squared plus y squared, that's the cone, and the sphere is z is equal to 2 minus x squared minus y squared. We want to find their intersection, and and whatever that intersection is going to be down on the xy plane. We could try to set them equal to each other, and then we'd have to square, and all kinds of other stuff might not be so pleasant. And so what we can do is, why don't we go ahead and go into polar coordinates, where x squared plus y squared is equal to r squared. So the square root of that would be square root of r squared, which is r, and this is 2 minus r squared for the sphere. And by setting them equal to each other, we would get r is equal to 2 minus r squared, and if we bring the r squared to the left side, that'll be positive r squared plus r minus 2 is equal to 0. And then we know that r, I think this factor is nice and easy, to r minus r, r plus 2, and r minus 1. So r equals negative 2 is not what we're looking for. R is equal to 1 is what we're looking for. And that gives us the radius of this circle. That gives us the radius of the shadow, of the shadow on the xy plane. Okay, so that will give us good ideas of what we can do with this. All right, now let's do part A, where we want dz dr d theta. And if we want dz dr d theta, we would draw a line parallel to the z-axis. We would enter through the region, through the cone. This is the cone right here. And so our z limits will go from 0, not from 0, from the cone itself, so that's r, to the sphere, and this is the sphere right here, 2 minus r squared. Your r limits, for this one we want to look at the shadow on the xy plane. The r limits here are just going to go from 0 to 1, and our theta limits go from 0 to 2 pi. All right. Now we're going to write this integral to find the volume. V is equal to the triple integral. We'll set the limits in here. We have a 1, and then remember that the dv will have an extra r in it. And we're going to write it in this order. So dz going from 0, oops, not 0, going from r to 2 minus r squared. dr goes from 0 to 1, and d theta goes from 0 to 2 pi. Okay, that is our first integral. All right. Going into our second type of integral, they want dr dz d theta. So dr dz d theta. So how we're going to do that? So r is going to be our first integral with respect to, take an integral with respect to, and the rate r is going to be the radial distance from the z-axis going outward. Now, if we follow this along, the radial distance from the z-axis going outward is going to go from 0 to this cone, but only up to a certain point here. Only up to a certain point. And after that certain point, your radial distance, we're going to go from 0 to the sphere. So it looks like we're going to need two integrals here. The two integrals that we're going to create, we'll create an r, z, theta set of inequalities for the first one. And then we're going to create another r, z, theta inequalities for the second integral. All right. The first integral, the r limits are going to go from 0, and then it's going to go out, like I said, to the cone for that first one. So that's going to be r is equal to z. We want to solve for r in those cases. So r is equal to z. And then z is going to go from 0. Now we need this intersection here where they intersect. So we have r is equal to 1. We got that from the intersection. And we can put r is equal to 1 either into this sphere equation or into this cone equation, and then figure out what z is equal to. And you see either case, if we put it in there, we're going to get z is equal to 1. So that gives your limits for z. And theta still will be going from 0 to 2 pi. All right. Now, after this plane, z is equal to 1, your r limits are going to change. Your z limits, your theta limits are still going to go from 0 to 2 pi. But now your z is going to go from 1 to whatever this top part is. I believe if this is the sphere over here, when x is 0 and y is 0, oh, it's not a sphere, sorry, it's I keep calling it a sphere, but it's a paraboloid. I was wondering it didn't have a square root here. So this is a paraboloid. Paraboloid, paraboloid, paraboloid. So paraboloid. So now your z is going to go from 1 until we hit the top of this paraboloid, which is going to be 2. And then your r is going to go from 0 to the edge of the paraboloid. And here we need to solve for r because we want it in terms of z. So we have z is equal to 2 minus r squared. R is equal to, that's z minus 2. Actually, it's better if we bring the z over to the right side and bring the negative r squared to the left side. So that's r squared positive, and then 2 minus z, and then you take the square root of 2 minus z. We're just dealing with a positive part because r is a radial distance and distance is positive, so we'll keep this positive. 2 minus z. Now, obviously, we have two integrals here, and this is preferred over this one. So if you have a choice, I would choose the first one. Always be choosing z first and then r and theta when you're doing a triple integral in cylindrical coordinates. It's just that this problem is forcing us to do it this way. So to do it this way, we will come up with a volume, and there's going to be two integrals that we have to do. We're still going to consider the r, except now we have a dr, dz, d theta. And this is going to go, the r is going to go from 0 to z. The z is going to go from 0 to 1, and theta is going to go from 0 to 2 pi for the first integral. And then we have to do another integral of the same thing. And this integral is going to go, r going from 0 to square root of 2 minus z. Z is going to go from 1 to 2, and theta is going to go from 0 to 2 pi. Okay, that's our second one. All right, the last one is asking us to consider writing this integral with d theta first, and then dr, and then dz, and then dr. And to do this, what we really have to note is that there are no particular relationships between theta and either of these variables. And so it's really just looking at this theta here and saying it's going to go from 0 to 2 pi, but that's independent of everything else. So we can switch to order here without doing, it's still going to be dz, dr, and then d theta, doesn't matter whether you do it last or first. And so here they're asking us to do it first. So I would call on this set of inequalities to set up our triple integral for d theta, dz, dr. And when we do that, our v will equal to the integral of 1, again, r, and then d theta. D theta goes from 0 to 2 pi. And we're following this lead over here, dz. dz is going to go from r to 2 minus r squared, and dr goes from 0 to 1. Okay, so this is our last integral, and it's, again, not preferred if you ever have a choice in doing any of these. The preferred method here would be the dz, dr, d theta for triple integrals using cylindrical coordinates. Okay, anything else could cause some more confusion that's not necessary, so this is it. But they want these other ones, and so these other ones would look like this. Okay, I hope that helps.